Go ahead and get started. So our keynote this year is Anshu Dubey, and many of you maybe know her, but for those of you who don't, the sort of technical part you need to know is she's a computer scientist in the Mathematics and Computer Science Division at Argonne National Lab, and also a senior scientist at large at University of Chicago. And I could go read her whole bio, but I always stop listening after that first sentence or so. So what I wanted to tell you instead was how I met Anshu, which was we're at a workshop maybe 5 years ago or so, and I was doing my normal chapel pitch, and like often I would sort of say all these things, and it wasn't clear it was really registering with anyone in the audience, and then afterwards Anshu came up and said, I really like what you're doing with chapel, I hope you're successful. And I said, oh, I wish you had said that out loud. And she said, people already think I'm crazy and want too much, so I didn't want to have it. But at that meeting, and since then, what I've learned is if you're in a meeting with Anshu and you're talking about programming, a question that will come up over and over again is, in your opinion, if I'm starting a new big application for DOE, what programming model should I do it in? And which is a very reasonable question to ask. And you know, people sort of hem and haw, and inevitably the answer seems to be, well, probably C++. And I remember at one of these meetings she said, no, not C++. I need a different answer than that. And that was very encouraging to me. So through that and other interactions since then, we thought she'd make a great keynote speaker for us this year. So,
Thank you, Brad, for giving me a chance to get on my soapbox, because that's what you're going to hear. This is my favorite topic, and I can hold forth on it forever and ever and ever, because I have long held that it's the software design that needs to happen first, and based on what that software design comes up with needing is what the programming abstractions should deliver, rather than a cool idea that people have, because many cool ideas don't pan out. Anyway, so since about 2011, I've been thinking about what software design should look like with increasing heterogeneity. And for I think about 6 years or so, I felt like I was banging my head against a wall. Because everybody would say, yeah, that's a great idea, but how are you going to raise money to do this, and how are you sure that you can pull it off? And then the ECP project happened, and for many in the computer science community, that has been not so good, because it's not giving, it's taken away a lot of the funding that was funding the computer science research. But for me, it's been great, because it gave me a chance to pretend to be doing an application and performance related work, but really it gave me a chance to think more about software design and actually implement it. And so that's what I'm going to talk about today. So making the most of my opportunities. Okay, but because the next slide is too good to pass up, I'll start by saying that. And that's my setting the stage. In terms of what should my ideal computational tool do? Everything, really. Scan my brain, figure out what I want, scan the literature, figure out the equations, auto-generate the code, run it, analyze the data. I'm happy to present the results.
I thought we called those grad students.
Yeah, good grad students.
Yeah. It doesn't quite work out that way, unfortunately. A very ambitious postdoc, maybe. Anyway, so, but since the programming models are not so obliging, let me reduce the complexity by several orders of magnitude. And that is the question that Brad already posed, so he stole my thunder. If we were starting a new multiphysics exascale software project today that expects to have a long-term use for scientific discovery, how should we design the software? And unfortunately, we still don't have an answer to it. I think I do have an answer for one class of problems, but then that's my very, very biased opinion of the whole situation. But the reason why I like Chapel and its design is again reinforced today when I heard Brad's state of the language, state of Chapel in the morning, and the design choices that they're making and the things that they're prioritizing. what that led me to realize is that chapel designers seem to think the way I do. I like the abstractions and the design, and part of this talk will be explaining to you why I think that that is the case, and why I would really like to see that if there is ever a Flash 6, that I would have the opportunity to do it in chapel. Okay, so software science code development follows this sort of a life cycle, is that we start out with a physical world, that there's some phenomena in physical world that somebody in a science domain is interested in. They take that and they make a mathematical model out of which is some equations. I'm not saying partial differential equations or what sort of equations, some equations. And then they discretize those equations to make them usable on a computer. And so that discretization may be in form of, and the reason why I'm using mesh and particle, I want to emphasize, is without any loss of generality. I'm using them only because that's the discretization that I'm familiar with. So you do the discretization, and then you write numerical algorithms for these discretizations. Then you do the implementation, and at the same time, if you want to have any credibility in the science that is being done with these equations, then there is a very important part of it, and that's validation. Because validation is what tells you whether your model is actually capturing the phenomena that you want it to capture, all right? There are some feedback loops, because the process never just goes linearly like this, because many a times you make your approximations in the model and you find out that the important characteristics didn't get captured, so you go back to the drawing board and you tweak the equations. Similarly, when you're doing implementation, it's not just checking for accuracy and correctness, it's also checking for accuracy, stability, and whether it gives you enough fidelity answers in the regime that you're interested in. An interesting aspect of this is the domain expertise that needs to be talking to each other throughout the cycle. So there is the domain expert that changes the phenomena of interest into a model, a mathematical model. There are the applied mathematicians that take these discretizations and develop numerical algorithms for them. There are the applied mathematicians and software engineers, actually I missed that here, that do the implementation and verify the accuracy and stability. Oh, there is the software engineer, so my animation is just a little out of order. And then there is the domain expert involved in doing the validation against what the phenomena in the physical world. And all these people need to talk to each other in some sense if the set of equations and the phenomena is anything non-trivial. And so you can already begin to see the complexity there is, because we're talking about people coming from very diverse domains that need to cooperate, communicate with each other and cooperate with one another effectively to create an ecosystem which can be used to do science. But there is more. If you're doing this work on high-performance computing platforms, then there is also the performance that becomes an important aspect of the whole endeavor, and that requires then some more intervention from software engineers and optimization experts, right? So with that, let me move us with this in mind. This is always something that needs to stay in the back of our mind, is that this is the process that needs to happen for the computational science to deliver any results in any sort of a credible way. You had a question?
I hope it's an accident that we no longer validate in this version of the screen rather than once we start performance tuning, we stop validating, which is the way it works.
Right.
But I hope that's
This is true. No, but in some sense, actually, no, this is by design. It's because the performance improvement is, if you have a verification already, a verification test, then performance improvement and meeting that verification test is good enough for validation.
Okay.
Right?
So you're saying that leaving out that edge was deliberate?
Yeah,
Yeah. Okay.
yeah.
So you validate against your previous software test suite, but not against the physical world again.
Yeah, you don't
Okay,
need
okay.
to. Because once you verify that your model is what you wanted the model to be, then when you're actually doing the performance tuning, you don't need to keep that loop going. In fact, that becomes an impossible problem to solve in its own way. Okay. So with that in mind, now let me move to what does it take to architect scientific codes. And I'll start out by saying stating the desirable characteristics. So the desirable characteristics are, one of them is extensibility, because use cases are never the same. In my 20 years of working with scientists, there have been no two simulation campaigns that have used identical code. And usually the changes that are non-trivial from one simulation campaign to another. The second one is portability, because the lifecycle of software, especially a multiphysics software, is several times the lifecycle of any platform, which means that if you don't want to walk yourself into a corner, you need to be able to move the code easily and quickly to new platforms whenever they become available. Performance, because all resources need to be used well. And maintainability and verifiability, because of this very important aspect is that credible and reproducible results. Our field in particular has been lax in this regard, and that is beginning to change, and that's a good thing. But that places another constraint on the development. In some way, what do those things mean? Extensibility means that one should have well-defined structures and modules and an ability to extend them, which through encapsulation of functionality, so that if you've done your design well, you can bring in a new functionality properly encapsulated and need to make small amount of change to the overall code base in order for it to be incorporated into the code. For portability, we need general solutions that work across different architectures, different platforms. Not custom solutions are not really an answer. For performance, it's one needs to focus on general things like spatial and temporal locality, minimizing data movement, and maximizing scalability. For maintainability and verifiability, the code needs to be clean. It needs to be well architected. And there should be comprehensive documentation and testing for the code. All of these are absolutely necessary. They're necessary but not necessarily sufficient conditions. Why is that challenging? Because the requirements are at odds with one another. So extensibility, if you want to use many different solvers, and the data layout of one new solver that you want to add may not be consistent with the solvers you had before, and all of a sudden you have the need for maybe a copy, a transposition, and that makes things hard. There are many corner cases that happen in physics, but the biggest problem of it all is that the real world is messy, and therefore anything that models it becomes messy by association. Because if encapsulation only works so far. If you have to have lateral interaction between two different solvers for the physics to be captured right, you have to do them. There is no way around it. For portability, there is so this is actually detailed much more in a slide later, but there is the two axes of heterogeneity that we are dealing with. There is the platform heterogeneity and there is the solver heterogeneity. And if you try to have a different version for each class of device in platform heterogeneity, now you already have a combinatorial explosion. And if you combine that with the different kinds of solvers you need, it just becomes a humongous problem. Performance is that many of our solvers have low arithmetic intensity but have absolutely sequential dependencies, because of which there's only so much you can do to do fusion and so on and so forth. And for maintainability and verifiability, there is no real technical reason. The reason there is much more sociological. It's the set of incentives and the priorities, and actually, I'll take that back. There is a little bit of a technical problem also, is that designing good tests is hard.
When you say incentives, are you referring to like our community values, performance?
No, I'm talking about the domain experts are under pressure to produce papers.
I
Their
see.
engagement with software development doesn't give them any rewards.
Okay.
And performance, I'm not sure that that matters so much anymore these days. It
Okay.
used to be much worse about 5 years ago, I would say, but it's not so anymore.
Okay.
So what design approach can we take to tame this complexity? And this is an approach that we have taken with Flash from about 2005, I want to say, from Flash version 3. It is that you recognize that there are some parts of the code that need to change much more rapidly than other parts of the code. And that there are some parts of the code, and that is the infrastructure, that needs to be given a lot more thought. So things that are undergoing research almost on a continuous basis, things like models and numerics, they are a different class of capabilities that you develop in the code from the class that is discretization, I/O, and parameters, and so on and so forth. So the thing is, treat them differently. Okay. The second part of it is that the parts that are subject of research, usually models and numerics, have another feature to them, and that's that they are mathematically complex but are usually logically simple. Whereas the infrastructure, data structures, and movement are mathematically simple but logically more complex. And so the thing to do then is hide one from another as much as possible. But in addition to that, then both of these classes of problem need to have certain common features to them, and these are that they should be encoded in logically separable functional units of computation as much as possible, encoded into a framework. The frameworks, of course, should be differentiating between public and private. That's just common sense, object-oriented programming, and that they should be interacting through interfaces. And so this approach is what we have used in Flash, and schematically it looks something like this. So this half is the infrastructure development, and that half is the physics capability development. Notice that if infrastructure is developed well, then there are only very few places where an interaction needs to happen between the new physics capability being developed and the infrastructure. And most often this infrastructure will not then need modification in order to add a new capability, because the capability can be prototyped, checked out, whether within the framework or outside of framework, but then as soon as its interface is defined using which it can interact with the rest of the code, it can be brought into the code. Okay, so the design philosophy then is that the infrastructure design, one should take time to discuss, iterate over requirements and specifications. I know that it has become a fashionable thing to say that agile methodology applies to scientific software development more than anything else, and I disagree with that when it comes to software architecture and software infrastructure development, because agile is completely wrong for this. You really need to sit down, debate over design choices, build prototypes, discard them, and finally put down clear and detailed specifications and build the infrastructure. Only when you have enough confidence in your infrastructure that you should start to add capabilities to it. This goes a long way towards keeping the rest of the project's code development easier in the long run. This lesson was learned the hard way by the Flash team, is that keeping the end user involved is critical. Anytime you don't keep the end users involved, you may use your imagination to figure out what they would be wanting. Half the time that turns out to be wrong. They want something completely different. Also, this is a critical part. Remember I said that designing tests is hard? Well, designing tests without the involvement of the domain scientists is nearly impossible. Designing effective tests without domain scientists is nearly impossible. So keeping them involved is very important. And also, if you don't, and they sometimes have ideas that wouldn't have occurred to you because they know things about the domains, the shortcuts that are possible and so on. And so if you don't involve them, then you leave out those opportunities in the design process. The second thing that we learned is that simple is better. And for example, in Flash's design, whenever there is any time that we have to do flexibility versus making that particular feature transparent to the user, we always opt for flexibility, because we do not believe in this philosophy that people should not need to know what's going on in the internals of the code very much. And hierarchical access to feature. And what do I mean by hierarchical access of feature? And in fact, this is what I would like all of the system software to offer to us application code developers also. It is that graded access to features within the software. So the thing is that this is what the infrastructure looks like. There is an outer layer, there is an intermediate layer, and then there is the real core of the code that exists. Now, at times, it is useful to be able to access that core and be able to use it without having to dig through all of the software, all of the package. And that's possible only if the package itself is exposing interfaces at various degrees of granularity to the end user. And so it's important to take into consideration the features, the deep down features of the software that may be useful to the end user, and bring them out and expose them to the end user. And so basically this is the wrapper layer of the physics that can then interact with all of these interfaces at various levels, and these are sort of important all along. And I will give you a very simple example, is that so I'm very familiar with AMR, adaptive mesh refinement. Adaptive mesh refinement is you put more resolution where there's more going on in your physics, and you put less resolution where there is less going on. Now, most of the AMR packages come with a standard way of tagging the parts of the domain that need to be modified. And that's usually deep down into AMR packages. But almost always you need some sort of a customization to the refinement criterion that you're using. And so if there was an AMR package that did not make that low-level functionality available to the end users, it would be a pretty much useless AMR package to the users of that code. Okay. So now I will move from generalities to specifics of Flash, because I want to tell you about our design. I'm rather excited about it. This is Flash. So Flash is basically a multi-component, multi-physics code. You can never build it as a whole binary. You never build the entire code all at once, because what it has is it has a bunch of components. Some of those components are multiple alternative implementations of each other. They just follow the same interface but maybe solve for different regimes, and therefore when you're solving a problem that needs to use one solver versus another, you can pick it up. And it has, over the years, many capabilities have been added to it. So now it has become a community code for upward of 5 scientific communities. They include astrophysics, cosmology, high energy density physics, computational fluid dynamics, and biomechanical systems. As you can see, these are pretty diverse set of communities also. So these are some of our simulations that have been done. This is a supernova explosion. Type 1a supernova, this is a core collapse supernova, these are all laser experiments. This is just a simple turbulence problem. These are cosmological simulations, and so on and so forth. And this is just a representative set of the kind of science you can do with Flash. Now, what has been going on with Flash is that we have this positive feedback loop cycle, in that we have more scientific understanding, which means that we then we add terms to the model. It becomes a higher fidelity model. But what that means is it needs more hardware resources to run, and also it may need more diverse solvers. So you create more diverse solvers, you use more hardware resources, you get more scientific understanding, and the whole cycle continues. The other thing is that many of these components are under constant research, and the software is continuously evolving. So, and also this software, most of these simulations do run on the high performance computing platforms, mostly leadership class platforms, because these problems do need those kinds of resources. And the last one is that all use cases are unique and different. So these are the challenges that Flash faces, in that it is serving a community. At the same time, the code is in constant state of flux, as is the user community, and somehow these two things have to be resolved and figured out. So before I launch into the actual architecture of the code, here are some of the code basics. As I said, there are units, there are encapsulated functional units. Each unit represents a class of functionality. It is not really truly a class, it's just a class of functionality. Units are combined and composed to form applications. There is a setup script. It's a Python tool that parses config files. And I will go into config files in a bit more detail because they are the key to some of the architectural features of the code that I'm going to talk about. But they basically, for now, it's enough to know that they encode the meta information about the unit or the subunit or its implementation that is getting included in the setup of the application. So it picks specific implementations of the unit and composes full application. And composability implies that any of the implementations can be picked. The code is mostly written in Fortran. There is some C. It's about 1.5 million lines of code now. It is portable, and until recently it was also performance portable because we had a single machine model to which we could program, and we had done division of labor, parallelization on one part, and memory access optimization on the other part, and all was good. If you made it work well on one platform, it would work well, more or less well on other platforms also. That has changed, and so we've gone back to the drawing board. So our design considerations have been encapsulation and interfaces that encode into separation of concerns, extensibility, locality, composability, orchestration, and cost accounting. The only thing that I'm not going to talk about today much is cost accounting because that's a whole big topic in itself, on its own, but it plays into the orchestration part, and I'll get into that a little bit. So encapsulation, the way we look at encapsulation is that we think of the code as a whole domain with many operators. Each of the physics is what I'm calling an operator here. So there is this whole physical domain onto which we apply operators one after another. The code so far does operator splitting in the sense that each physics solver can be invoked one after another. And that may not remain true in future, I've been told, but for now that works, and so we leave it at that. There is the spatial decomposition, and then we think of it as a virtual view where each domain section is a standalone computation unit, and because majority of our solvers are explicit, that works. We have the cells surrounded by the halo of host cells, and as far as the physics operator is concerned, it cannot differentiate between that domain section and the full domain. So it thinks it's operating on the full domain. All right. Then the virtual view on the side of functional decomposition is that it is a collection of components. And so parallelization and scaling optimization happened through this virtual view of domain sections, and memory access and compute optimization happened through this virtual view of collection of components, and each one of those were fully encapsulated entities. The second one I said was extensibility. So this is what a Flash unit typically looks like, is that there is the unit has an API, API has a config, and I will explain these config files again. And then through layers of wrappers, there is at the end of it an implementation, which is where the computational kernels actually sit. Driver is the special purpose unit. It is where the time stepping is implemented, and this is also what orchestrates the interaction among units, more or less, for obtaining the solution. So when we want to add a unit to Flash, a new unit to Flash, all that needs to happen is this unit is brought in, and the only change that needs to happen is that Flash driver needs to be modified to invoke the init, the do, and the finalize for that unit. And that unit becomes known to the code. The setup tool is smart enough to differentiate between the namespace and the Unix directory. So we implement our object-oriented framework using Unix directory structure. We don't use Fortran's object-oriented functionality, and that is because when the code was initially implemented, that functionality wasn't available, and people didn't want to translate the code to C++, so they built an entire object-oriented framework on top of this Fortran system, and we found it to be so good that we've kept it around. It has many useful features. It doesn't bind us and limit us in any way in terms of features that we want to add. Anytime we want to add a new architectural feature, all we have to do is actually add a little bit of functionality to our setup script. The best part of it is that because it is not imposed by a language, when we need to do a short circuit for debugging, we can do it. And that saves huge amounts of time at times. Okay, so this is all the change that needs to happen. Nothing else needs to change. Now supposing we wanted to add a subunit to an already existing unit, which means that a unit exists, but now we want to add some additional functionality to it. The change that needs to happen here is that Flash driver remains unmodified, but the grid API is modified because some new interface functions are added into the API. And perhaps the config file here will need modification, but that's all that needs to happen. So really the extensibility is built into the code in a way that it's very easy to add more functionality. Then we get to composability. So the composability is where we can, we are doing a division of labor whereby the framework, the AMR infrastructure, it handles the refinement, load balancing, and work redistribution. It retains meta information about domain sections. And what this allows is also to make things like load distribution and dynamic scheduling, etc., can be held under the hood by allowing for this kind of separation here in this in the architecture. And then composition happens whereby, so this is what we are doing for future, and composition happens where in the second half of it is where we are looking at abstractions at solver level, which may involve some code transformation, fusing and inlining, etc., for memory access and compute optimization. And this, for the most part, we want to leave to tools and compilers to optimize. But what we want to do with the solvers themselves is have abstractions and ability to express operators at a higher level. And this goes back again to something that Brad had mentioned in his talk earlier today about how an MPC plus MPI implementation is very, very, it dictates what needs to happen, whereas you don't really need to dictate what needs to happen. You only need to convey what is the result that you want happening. And that's really what we want with our solvers, to be able to express our solvers as. Okay, so that we don't keep any optimization blockers around. So we are going to do this through two parts of code transformation. Okay, one part of code transformation is familiar to people, where people are doing DSLs or other auto-tuning codes, etc., which is where you take the solver level kernels where actual arithmetic is going on, and then you use these tools to make platform agnostic code which can be translated through backends into the appropriate code for the target architecture. So this is the paradigm of write code once and generate optimized code for the target. For this, we intend to use a transpiler, and we're working with our collaborators at Tokyo Institute of Technology who are building this transpiler. And the idea behind this transpiler is that, first they had started doing a work of taking a code, a high-level language code, and producing LLVM IR, and then using that to build the compilers. But then they thought an IR doesn't need to be in that specific format. So instead of generating an LLVM IR, they started to generate the IR in Python. Okay, and what they did was they constrained Python. So some of the features that make it impossible to optimize Python code, they did away with it, and because they are the ones that are generating the code in Python, they can get away with whatever constraints they want to place on it. And so, and then they can use optimized code. It can be generated from there with whatever backend they want to do, whatever layers of things they want to do under it. So this has been going on for a while, and there is, it's an interesting concept, but that's not where the thing that we are doing is different. The thing that we are doing is that we also want to implement code transformation for high-level composition of operators. And this will not happen at compile time. This is not a compiler thing at all. This is going to be done during application configuration and communicated to, and communicating to the runtime in part. And this is what we call the orchestration system, where in addition to the config file, now we will have a task composer that will be used for consideration. And this is the extension of the original config files. Config file is effectively a configuration DSL, if you want to think of it that way, because the config files have Flash-specific syntax that is understood by the setup tool in order to put together the application as a whole. So a primer on how Flash framework configures application through the config file. So this is what a typical config file looks like. What this is telling the setup script is this is some physics unit, say a hydrodynamics physics unit, into which this config file is sitting at the top level. And what it's telling the setup tool is, I do need the driver, I do need hydro, I do need equation of state in this particular equation of state exists in many forms. There is the ideal gas gamma law, there is the tabulated equation of state. This is the equation of state generated with Helmholtz free energy. So this is telling it that I need that specific form of equation of state, that I need nuclear burning networks, and I need a composition in my simulation. And so this information is conveyed to the setup tool. Now setup tool will in turn go to all of these. It will go to physics hydro, it will do the similar parsing for physics hydro, and hydro will tell its dependencies, the unit that it needs to work on, units that it will not work with. They also, so this is just a snippet, it doesn't have the full functionality, but what is also encoded in here is the state variables needed by that particular unit, any actions that need to be taken at the fine coarse boundary to make that the solution consistent when there is an AMR going on, the runtime parameters that can be used to control the behavior of this particular unit, and so on and so on. These files can exist anywhere in the directory structure. They just encode all of this meta information about that particular level within the code. And the way then an application would be configured in Flash is something like this. So a particular simulation setup is where the setup tool starts to parse. So this particular simulation is the shock tube. So there is a directory for a shock tube simulation which will have said that I need hydro and that I need equation of state, ideal gas gamma law, and only those two need to be included, and this particular application is all set up. By the way, this is representing mesh. The grid is always needed. If you want to do a slightly more complex application, which is the cellular burning, in addition to hydro and equation, it needs a different equation of state, and it also needs the nuclear burning, which is the ordinary differential equation solver. So this is how that equation is. A slightly more complicated one is one for type 1a supernova, which is the gravitationally confined detonation model. And here, in 2 more units got added. It needs Lagrangian particles and it needs self-gravity calculation. So all of this is basically coming through by parsing these configuration files. So these configuration files are parsed. Also encoded along with that are the snippets of make file that sit in the unit. And so those are also combined together. And at the end of it, a self-consistent application is built just by doing this scanning. So the intelligence doesn't lie, the important thing to realize is that the setup script itself doesn't need to be very intelligent, because the amount of intelligence needed is divided between how the config file is encoded and how the setup script parses it. Okay? So setup script doesn't have to know all of the unit specific knowledge that needs to be conveyed to it. Okay, and I will go through this quickly now because I'm beginning to run low on time. But so basically this is how, So now we are extending that concept to what we call composer files. They follow the same philosophy as config file. What we are going to do is at each unit and at whatever level necessary in that unit, we will build these files in the code, and they will encode meta information about the division of work between devices, and the data movement that needs to happen between devices. So the idea is this, that we don't want the tool that is going to do this transformation for us to have the intelligence to know that this is the appropriate thing to send to this device and this is the appropriate thing to send to that device. Instead of that, we are letting the unit developer, who is the most knowledgeable person about that particular unit and its features and its idiosyncrasies, etc., to be able to encode that information in a way that a tool can parse, and it's going to be a part, something like a dictionary, which means that we just take code pieces and we allocate a keyword with them, and within the code it's just that keyword that sits there. So these are going to be a little more complex than config files, but not a whole lot more complex than config files. They will operate at individual unit level, which means that we are not imposing any specific syntax onto the developers of new units, and we are not imposing this requirement that a new unit coming in has to have this feature in it. If they want to be able to generate platform agnostic code and keep it around, then they can make use of this feature, otherwise they can forego it. So what this tool is going to be, we are hoping again that the same principle applies, that the intelligence of the system is divided between the composer files and the composer itself. And what it should ideally do is parse the meta information and produce executable code. So this is our vision, is that we encode for each of the units, we encode platform information, and this can be added on, just like the units could be added on as new platform becomes available. The platform related information can be added on. Solver information, which is basically we are dividing solver into smaller and smaller kernels. We can get away with doing it because now we have a code transformation tool that can do the fusion for us. And so we will divide it up into small functions and have the hints about this is the part of the code that can be offloaded to this kind of devices and will work well on this kind of devices, just encoded in there. Memory requirements, so right now our vision is, and time will tell whether we can realize it or not, is that any memory allocation that needs to happen between different devices can also be encoded as information. Kernels, and then the operation that need to happen with this kernel. So the task composer parses all of this information, digests it, and emits code like this, which is then fed to the transpiler, which will then generate a high-level language code that can be then fed to compilers and produce executable code. Okay. Another thing that this task composer will do is it will generate this kind of information, which is the runtime orchestration system. And what this is doing is it's just picking threads. So one thread to pack the blocks that need to be sent off to the devices, another one, some managing execution threads, some unpacking threads, and work is going back and forth between different devices, etc. So building the code, configuration will happen in 3 stages. The stage 1 is the usual running of setup script. We may have to enhance the setup script a little bit. In fact, I think we will have to enhance the setup script. Stage 2 will be run the task composer, and this is not the run in the sense of executing the code. This is still a pre-compilation stage. Okay, and then stage 3. So all these 3 stages are pre-compiler stages. So we do the configuration, we do the composer, we run the transpiler, and then we run the compiler, and then we run make as usual. So it's the orchestrator generated in the process will launch various threads that control runtime, may or may not interact with AMR asynchronization that is being developed in AMR itself. So we still have a lot of open questions. At this point, we have a very simple prototype of a simple composer, and we have sort of decorated code with comments that this is where we want the composer to intervene, this is where we want the transpiler to come in, and our collaborators are studying it, and we are trying to figure out what we can do with the system. But both our collaborators and us, we've given enough thought to it that we think that this really has a chance of generating a performance portable, somewhat future-proof code without having to do a whole-scale surgery of the code. Time will tell whether we succeeded or not. But here are the reasoning why we choose to do it this way is that we recognize that lots of things that people call difficult is not where the difficulty lies. Difficulty lies in other parts. For example, people say MPI is difficult. MPI is not. MPI is the simplest thing there is. What's difficult is decomposition. What's difficult is understanding the parallelism that is inherent within your code. Again, and also in parallelization, as in a lot of any other way in which you interact with the systems, neither or nor none is good. So neither size, I mean, all of the work should not be left to either size. There should be a cooperation. Because whatever is the model used, understanding the parallelizable structure of the applications and having constructs to encode that information, that understanding is what is needed. My favorite rant, by this way for the kernels, C++ is pushing a needlessly complex language that lacks basic structures that are necessary for scientific computing. But my real beef with C++ is that it brings out the worst in the programmers. They want to prove just how smart they are, and they write totally unreadable code. If people were disciplined, C++ is a fine language, but people aren't, and that just makes it an impossible kind of language to deal with. Maintainable code in clean constructs, and perhaps what we may end up doing eventually if our transpiler vision comes to pass is that we will just stop maintaining Fortran code altogether, and we will just start to maintain the Python code. It will be a lot more maintainable. And we can also, because we already have the configuration system to do alternative implementations, and we can pick these alternative implementations at any granularity, we can exploit that system in addition, so that wherever it's not possible to really have things like code transformation like transpilers work, we can actually do alternative implementations for those code sections and exploit the configurability of the code to use them. The advantage of this system is that all code can be compiled eventually with standard compilers. We will not need to have compiler technology ourselves. The Flash basic core team developers. We will have constructs for expressing parallelism at different granularities. Limited intelligence is needed in any one tool, because I think if we try to make one tool too intelligent, first of all, it becomes difficult to develop, and second of all, we need to have people with that expertise also around with us all the time. And the domain knowledge will be encoded in composer file, which means that will help with optimization. And I think this is the approach that Chapel Design seems to be taking, which is why I think Chapel Designers thinks the way I do. Questions?
Yeah, so it seems very familiar to me. Are you aware of a project it's called the Muse
No?
in astronomy? I think it shares many of the goals actually. So it's a Python framework, and they try to connect all kinds of modules and run huge simulations. Well, in astronomy then, but cloud forming and then small particles and they have also configuration.
Astronomy? Are you sure?
Yeah, and also they use configuration files, but they have instead of types they have units, and so they can express domain knowledge in terms of units.
So then I need to look at this one.
Yeah, I think so. It's from Simon Portuguese Swart.
Okay, I'll take the details from you. I really do need to look at this one.
Can I ask another?
Hmm?
Yeah, and another question. So, if you have those units, of course, modularity is always good, unless you have something that is cross-cutting, and you need something that another module has and recomputes, and you want to fuse it at some point. It can also happen in these units that you just defined.
It does happen.
Yeah, and that seems...
So this was a simplified view that we have had situations where the lateral interactions need to happen, and for those units we've had to design around them, and I can talk to you in more detail about it if you want. And one particular one, for example, is the Lagrangian framework, because it needs to interact in the middle of whatever calculation you're doing in order to advance, and so the interface needs to get more complicated, but you can still, for the most part, we've been able to avoid it. It's not clear to me that we can continue to avoid it, because so far we've succeeded in keeping operators split. When that abstraction breaks down, I think we will be challenged a lot more. I think Vivek had a question, yeah?
Yeah, so you had mentioned earlier that data layout you saw as one of the challenges for extensibility. So how is that addressed, like if different units have preferences for different layouts, especially if they're implemented in different languages and so on?
So this is memory requirements that encompasses the data movement, and so again that is what we are going to handle. See, if data layout needs to change, it needs to change. So the thing that I didn't talk about in more details here, which is also a part of this whole ecosystem, is the cost model. And so in addition to all of this, what we're doing simultaneously is also building a cost model for various expenses that are there in running the code. And the code is instrumented, so every time you run it, actually that data is generated. And so our vision is that we will build a database of various ways in which the code runs. And using that, we would do the cost-benefit analysis. So if the cost of transposition is going to be amortized, we will figure out whether changing the layout is more advantageous versus rethinking the calculation, etc., depending on how much work needs to be done after transposition. Michelle, question?
Okay, so we've already touched on this a little bit. This idea that you want to keep the operators modularized separately, okay, and that shows up in a lot of these kinds of codes, these simulation codes. But then when it comes to doing optimizations, you want to fuse those operators, and when you fuse those operators, you also want to improve performance, you'd like to reduce the amount of temporary storage used between those. So how are you approaching that in this transpiler approach that you're taking? Like, how are you indicating essentially the in and out data of different operators so that you can figure out how to get rid of temporary storage and whether
So the
using
temporary,
operators is legal?
so first of all, at least in the physics that works for Flash and this operator splitting, the fusing of operators there are very few operators that you can fuse while retaining correctness. And that's because this is an AMR code, and therefore the ghost self-fill becomes a global operation. And at this point, at least, we think that resolving all the dependencies that go with the co-self-will operation in addition to everything else is not going to buy us a whole lot. And but some of the kernels are have enough work in them that their own different sections can be fused and generate a lot more work. So, and that's why we are sort of handing off, so the transpiler is only going to work on individual kernels within an operator. So the idea is that in the composer, we have these tasks, the task composer, it's the global operators, the global operations that need to happen that bookend the operations that can be optimized in any way. Okay. And so they communicate their temporary storage requirement, but usually in the model that
in
we
the
have.
configuration file here,
No, that will be in the composer file.
or in the composer file? So
Yeah, configuration file only knows about the permanent storage.
So in the composer file, you have a way to specify what the temporary storage is between various
Needed, yes.
various pieces of a particular operator.
Yes.
Or something like that.
Yes.
Okay.
Yes.
And are you able to take advantage of that in some
I don't
cases?
know yet because we are in very early stages of actually even prototype implementations.
Mhm. Okay.
But we've just sort of sorted out the design itself and we're beginning to implement it. And so even though at the moment I don't see any roadblocks, but I'm sure they'll come up. And I'm sure we'll have to change the design in some places and we may not be able to realize all of it. You had a question? No,
Oh,
you.
I was going to follow on with Michelle, so I apologize for the ring. I just put it to a higher level of silence than on my phone. Thought I had enough people ruled out already. I apologize if you hit this. With regard to some of the things Michelle was saying and Vivek was saying, is the actual specification of, say, how to fuse those things, is that something you envision in one of the tools or something you envision being something one of the performance tuning programmers would specify?
Not even the performance tuning programmers. I think this is what we will train our unit developers to do.
Okay. Okay, so they'll talk about how to actually fuse.
Not
those
how to
kernels?
fuse, but just to know when it's possible to do the fusion and let it be encoded
Okay.
in the code.
Okay.
So I think what's interesting when I see you talk about this is that I think when we hear about DOE having million-line codes and things, we imagine it all being very monolithic and sort of, and of course you've shown that no, it's sort of all stitched together very dynamically and it's very attractive. And something I wondered about during your talk, we were talking about interoperability earlier, and there were times when I thought, oh, maybe if one could wrestle funding out of someone, we could write a unit or a subunit in Chapel and sort of wed it into all this. And there were other times when I felt like, no, that probably wouldn't work out.
I think the framework in Chapel would work out much more easily.
But given the existing framework, would it be possible to write a Chapel unit and have it live alongside all the other units?
Yep.
Yeah, okay.
Yeah, absolutely.
Any
So
other?
the unit can exist in any language.
Okay, that's what I hoped. But then at
Yes.
times with the stitching, it became less
Yeah.
clear to me.
Because
So,
the
okay.
point is that the executable part of a unit has nothing whatsoever to do with the config files.
Mhm.
So even if you wrote your unit in Chapel, you'd have to provide a config file with all the necessary meta information. And then you can separately then we'd have to let the make system know about Chapel compiler also, and then it'll all proceed.
Okay, thanks.
Yeah.
So how do you actually do the communication? Maybe I just missed it. Like,
Communication between?
the units. So is
The
there-
communication between units is through the API.
So, but what does the API? So it's just send.
So the driver will say, call hydro init, call hydro do, call hydro finalize.
Okay. And is there also some, can you message also in, so if you have units that need data from each other in lockstep, for example, is such a thing possible? That you need to-
So I think we need to talk offline at greater length, because the way we manage data is that the units, physics units themselves don't own the data. The data is completely owned by the grid unit, which manages the mesh, and the physics units request the data when they need it, operate on it, and return it to the grid unit. And therefore, this is how the lateral interaction also happens, is that each unit also has interfaces for possible lateral interfaces that need, interactions that need to happen, and sometimes we choose to pass the data as arguments. At other times we just pass the information about, meta information about which part of the domain we're operating on, and we can let the unit that's invoked ask for that data by itself. It varies depending on how much of coupling is needed between them.
And on different machines then?
So this is the part where we are speculating a lot more. Okay, because this is the part where we are saying that if I were to say that so far we know that burn unit works really well on the GPUs. And so what we are saying is that in the burn unit we can say that if you have more than these many number of species, then you can offload it to the GPU. And that will just be encoded in some way. So, and then a corresponding orchestration system will be generated by the composer for that.
We're out of time, so
All right.
thank you very much,
Thanks.
Anshu, for the talk.